Well, thanks everybody for coming out for the last session of the day. I understand there's going to be a party when I shut up, so I'll try to do it right on time. If I fade away or start mumbling or you don't know what I'm talking about, just wave and interrupt me. It's the beauty of a live talk. So, I want to talk to you this evening about Akka in a little more of a concrete context. If you heard Jonas's talk earlier today, he spoke of a lot of the foundational structure for what I'm going to talk about, almost the implementation of. So it meshes very nicely. There's some code behind this, so there's something to look at when you go away. And I'll try to leave time for some questions at the end. There's a fair bit of material, so I'll steam right along. What I want to talk about is easy scalability with Akka. Akka has this promise of high scalability. What does that mean? How do you get it? What kind of patterns can you apply in a concrete sense that can actually get you in that direction? And I hope to prove to you that that can actually work, and I'll show it to you. So who am I, first of all? I'm Michael Nash. I'm with Bold Radius Solutions. I'm their VP of Capability. We're a TypeSafe partner. We have a great relationship with TypeSafe. We're Scala, Akka, Play specialists. We enable our clients to adopt the platform. We have offices all over North America. We're still expanding. That's my Twitter handle. I've been working with Java since it was called Oak. So, not working? Aha, how about now? Thank you. That's what I mean by interrupt if stupid things happen. Okay, so I've been working with Java an embarrassingly long time, back when they called it Oak, I think is when I started, and I've been working with Scala about the last 6 years. And I've had the great fortune to be in a position to do a lot of projects with Akka and Scala and learn a few things, what works, what doesn't, and a surprising number of things work. So what are we going to talk about? What are you going to know 45 minutes from now that you don't know now? What I hope to do is give you a bit of a background onto what we call distributed domain-driven design. You've probably heard the term DDD, domain-driven design. Distributed domain-driven design is the term that a lot of us in the industry have started using for a new pattern, an extension of that across distributed architectures. What is it? How do you apply it? How do you turn it into your project? What's CQRS? What's ES? All sorts of other interesting three-letter acronyms. How Akka does this? How does Akka fit with distributed domain-driven design and CQRS and ES? What's different in a distributed domain-driven design project? How does it contrast with an ordinary project? And how does that kind of, the really interesting question for me is, how does that kind of project scale compared to an ordinary project, even one using all of the same technologies on the same hardware? What does the real test tell us? So let me define a term first. Scalability. We throw that term around. But it's important to differentiate, I think, a little bit. Scalability is not performance. They're related, but they're not the same thing. Performance increasing means your response time goes down on a request. So if you send let's say you have a REST service, you send a request to it, your response time gets smaller as a measure of increasing performance. The ability to scale means that improving capacity, putting more resources into the puzzle, gives you the ability to handle a larger and wider load. So they're related, but they're not the same thing. And just increasing performance doesn't necessarily give you more scalability. So scalability can go in two dimensions. What's called vertical scalability, scaling up, a bigger box, basically. Put more memory, give me more CPU, give me a larger Amazon instance in our case when we test things. Or scaling out. We're going to be talking about scaling out primarily. Scaling out is more boxes, actually adding more systems, so a distributed system. And adding more nodes to that distributed system to get the scalability. So, Akka, we throw this term around. You've probably heard it a few thousand times here today and yesterday. Akka is really an implementation of the actor model, which existed before Akka, for the JVM. In one sentence, it's a share nothing, distributed, message-driven compute model. And all of those words have a meaning in there, but we're going to concentrate on a few in a minute. There's a Scala and a Java API for Akka. And if you know anything about other distributed systems and languages, it's a fair bit like Erlang or Elixir processes, only better. There's actually some improvements. Another important little keyword I'll mention, and you'll see what I mean by this later, is that it is distributed by design. So location transparency is part of the design of the actor model. You shouldn't care where actors are. Local is an optimization. You don't need to serialize and deserialize when something's local. So that's what that means. You'll see that buzzword on a lot of the Akka doc. I'm also going to talk about some acronyms, CQRS and ES. CQRS is usually thought of, there's a couple of definitions, but mostly it's called Command Query Responsibility Segregation. And really that's an incredibly complicated way of saying separating the read and write paths of a problem. That's really what it's about. How you do that is dependent on your implementation. There's a couple of common patterns. Again, I'm going to show you one. But that's really separate read and write. And I'll show you again what I mean by that. We're also going to talk about event sourcing. Again, you hear the term event thrown around a little bit. State being built from a journal of events is event sourcing, in essence. That's, again, the one-sentence description. Now, you hear me throw these two terms back and forth. One doesn't actually need the other. You could do CQRS without ES, you could do ES without CQRS. We're going to blend them together and make a particular kind of recipe here, but you don't have to do it that way. So event sourcing. Let's drill into one of these in a little more detail. Basically, event sourcing is all about saying the delta of a particular state. So let's say we're talking about a bank balance. Rather than saying my bank balance is $50, you say my bank balance went up by 5, went up by 5, went down by 2, went up by 5, went up by 20. Those are events. Each of those things happened. They happened in the past. They're done. Those are the events. Writing them to a journal and then reading them into something which then computes your balance is effectively the essence of event sourcing. That's event sourcing 101. There's lots of little nuance around it, but that's really all it boils down to. Straightforward enough, right? It's actually, interestingly enough, how most databases work on the inside, as Jonas alluded to. Now, CQRS, on the other hand, is just a little more complicated. And remember I said separating the read and the write side of a problem. So what that means is separating your write side by considering commands separate from events. A command is something that you're asking a system to do which may or may not succeed. So if I say, attempt to increase my balance by $5, or better, attempt to decrease my balance by $5. If my balance is $4, that command fails. So a command is a request for something to happen in the future. An event is typically thought of as something that's happened. It's done. So if you have a write model, you're sending it commands and saying, please try to do this, please try to do this, please try to do this. Validations may apply, rules may apply, they may or may not actually happen. An event, in essence, can't be rejected. It's something in the past. You may not take any action on it, but it happened. There's nothing you can do about it, it's done. So separating those two concepts and saying we're going to write commands and we're going to read from a separate piece of code a model from events, which as you can see is very similar to event sourcing, putting those two as two separate paths, that's CQRS in a nutshell. Okay? There's a 2-day course in CQRS, 2 sentences. It really is that simple in many ways though. You know, like anything else in software, the implementation is where the devil is, but we'll talk about implementation in a bit. I'll show some code. Everybody with me so far? This making any sense? Okay, good. Somebody nodded. I'm going on. So domain, I throw this term around too. Domain-driven design, distributed domain-driven design. Domain, let's make sure we know what we're talking about. Your application's domain is the bit of code that relates to the problem. It's not the plumbing, right? It's not how you solve the problem with, you know, database or drivers or any of that. That's plumbing. That's infrastructure, as we call it. The domain is, for example, I say here, if you have a payroll app, then things like employees, benefits, pay stubs, those are part of the domain. They're not part of the plumbing. So that's what I mean by domain. So distributed, let's add a D. Distributed domain-driven design is, it's a well-known technique. It's been around for a while. I'm sure a lot of you have probably heard of it. It's not only for object-oriented systems. That, I think, is a common conception that I disagree with. I don't think it's only for pure object-oriented systems with mutable state. I think that object-oriented and functional are not an either-or choice either. And I think an awful lot of people that work with Scala agree with me. Distributed domain-driven design, as it happens, is an incredibly natural fit with the actor model though. Because it's interesting, people think of the actor model and Akka and, you know, actor implementations as about distributed or parallel or concurrent. They're really about containing state to some degree. And that's actually their more important attribute. Again, I'll show you what I mean. So how does that contrast? What do I mean by that compared to traditional domain instances? Traditional domain instances is your typical update in place model. You have a record in a database that says bank balance, you have a transaction that says increase that by $5, you take away the $0 that's there now, you put $5 there, right? Update in place. That implies a blocking operation and it implies reads and writes going to the same place. Because when you want to know what the balance is, you go to the same record and you read the $5, right? This has problems when you start to scale and distribute. Specifically distribute, which is how you scale. So I call that a non-distributed domain. And basically it's your traditional CRUD domain. Your create, read, update, delete. Horrible acronym. Anyway, reads and writes to the same data store, database I'm using here, but it could be a file system. It's always consistent. This is one advantage of a transactional system. You can't get two different answers. You can't get, I've got $4, no, wait, I've got $5. There's always one single instance of the truth. And typically it's scaled via multiple identical replicas of the same application. So in other words, you load balance over HTTP, you fire up 3 or 4 different copies of your application, maybe you round robin or randomly assign the next request to one of those instances, but you all talk to some common store that has to be synchronized on the back end, or else you'd all get different answers. So the bottleneck in that, and the thing that limits its scalability eventually, is, as Jonas pointed out earlier today, contention. At some point, even if you have an in-memory store, you're going to contend because you're reading and writing the same piece of information. So at a high enough volume of scattered reads and writes, you're going to have a problem. At what level of scale you have the problem is really the only question. That's the vertical scalability. You can use a really fast computer and push the problem up a little bit, but you can't make it go away completely, and certain levels of scale will be out of reach. Okay, so this is what I'm talking about, I got ahead of myself. When we scale the traditional model, we throw multiple servers at it, right? We say, okay, we're going to distribute this across 3, 4, 5, 10, 1,000 servers. So there's more than one copy of each domain instance. Again, I'll talk about some detail of that. Each copy must read state every time in order to be consistent. There has to be a shared resource somewhere. Each must write fully to the same shared instance of a data store. And scalability is therefore limited. So it kind of looks like this. You've got an HTTP load balancer. Let's say we're talking about a REST-based service, right? Which we often are. I think we've all probably written those. We've got an HTTP front end that perhaps caches. That's one way to up your performance, not necessarily your scalability, but maybe your scalability a little bit. We have a load balancer that says this request goes to that node, this request goes to that node, but it doesn't matter which node I hit, they're all identical. And then I have my business logic running on the back end with what I'll call transient domain instances. In other words, let's say it's a customer record. I read the customer record by reading state out of the database. I have that instance of that object for a moment. I do whatever it is I do to it. Perhaps I write something or I read information from it, and then that instance is no longer valid, it's thrown away. That's a transient instance. And in the back of this somewhere there's a database. That database, by the way, might be distributed itself. That's okay, it might be replicated, not necessarily distributed. Those are two different things. So what's different? We've all seen that pattern. I'm preaching to the choir. What's different with Akka and DD? I always forget one of the Ds. Well, wouldn't it be nice if you could just keep all those domain instances in memory? I mean, we've heard memory's cheap, right? Not necessarily all of them in memory, but it would be great performance-wise, right? Even if you could do the writes to memory, that would be easier too, because of course writing to memory is what, 1,000 times faster still nowadays? But how do you deal with the volatile nature, right? It's going to go away when you shut the lights off. An event journal maybe. So a picture of a system that is starting to look like what we're aiming for is actually more like this. If we have our HTTP API, and then we use Akka's ability to do what's called cluster sharding, and I'll detail that a little more in a minute. Then let's say we've got 3 nodes, little tiny instance of a system, and we have 15 different customer instances. Now, in the previous model, any of those 15 customer instances could be brought up and instantiated on any of those nodes. In this case, it's a little different. We're saying node 1, your job is customers 1 through 5. Node 2, 6 through 10. You shard in some fashion. You probably don't do it like this, but you say, okay, A through M is on that server. Some hash function says, here is the customer I wish to talk to. That will map to one of these nodes. Now this sounds a little fragile and bottlenecky all by itself when I describe it at first, but give it a minute. Behind those, there are journals, and I'll describe the function of those journals in the CQRS ES sense in a minute. So one problem is you probably have, well, you hope you have more than 15 customers, right? This is a tiny little model. You may have millions. That's probably going to exceed available memory even across a whole bunch of machines. So cluster sharding alone won't help you. What you need is the ability to say, okay, that customer has activity right now, and therefore needs to be instantiated in memory. Things happen with it for a while, and this is how you tune that and what your aggregate roots are depends on your particular domain, the right way to tune this. But let's say that a customer logs in, does a whole bunch of stuff, then goes away again. So you would instantiate that instance, keep it in memory for a while, and then you have to have a way to say, okay, I'm done. That particular instance, that customer's gone, he's logged out, take him away again. You do that with Akka. Actually, Akka takes care of that for you by what's called instances activating and passivating. So it's a little bit like this in old-fashioned flowcharts. If I've received a message, if I'm an actor and I receive a message and I'm not active, then rehydrate myself, come into existence. So there may be a delay there because now I'm reading an event journal or I'm reading a snapshot. There's two different ways to do it. And I'm saying, okay, now my state is now up to date, but I'm in memory. My mutable state is actually in memory. The immutable events have been journaled to disk, but the actual mutable state's in memory. Now I process the message, which may or may not involve a write to the database, different problem. Then I'm done. I stay in memory. But if I receive a timeout message before I receive my next activity message, there's a clock ticking in the system somewhere that says every 30 seconds, send a message. Let's say, it's a little more sophisticated than that, but like that. Then I passivate. I'm done. There's been no activity for a while, I just go to sleep. What that means is that only your active instances are actually in memory, spread across all of your nodes. So this lets you do the equivalent of paging in the old days and have only those instances actually have activity occurring to them in memory at any given moment. So this means that 1 through 15 customers could be 1 through 15 million, you're still okay. That's a perfectly reasonable number of domain instances. So we've gone barreling through a whole bunch of instances, talked about a whole bunch of ingredients, and we've talked about a whole bunch of different ways to put these pieces together that are available in the Akka ecosystem. Let's just review some of the ingredients we'd use for a real system, and then bring this down to concrete terms and actually show you some code. So we're talking about Akka with the Scala API in this particular case. No reason in the world you couldn't do this with the Java API. We're using the clustering, Akka clustering, and the Akka Persistence modules, which are two optional modules. We're using Cassandra, a very modern database, and the DataStax driver. There is a type-safe activator for this template, by the way, which I can give you the URL to afterwards. So again, let's review what's different about this compared to the traditional implementation. We say now that our domain instances are transient, they're in memory. So they're not, the representation of a customer is not given by a record on the disk, it's given by an object in memory. Now, in the traditional model, you would replicate that information on disk into memory in some fashion, ORM, let's say. So it's memory resonant when it's in use. Reads and writes don't contend for resources because we're using that CQRS ES trick. And the cluster can actually be grown until the number of domain instances per node, so remember it was 1 through 5 customers, if that equaled 1, then new instances of nodes would not help you, scalability-wise, when you think about it. That's a pretty high number. If you've got 15 million customers, that means you need 15 million nodes. Not in my AWS budget. So what do you get if you do this? And I hope to be able to prove it to you. What is this supposed to do? The idea was easy scalability, right, with Akka? So we're supposed to get scalability. What that means specifically is that we can add nodes to our group of nodes that we're paying for on AWS, let's say, and we should be able to handle higher load. Ideally, we can do that on the fly. Here's some more nodes, go faster. Here's fewer nodes, go slower. Or handle fewer users, more like. It's not exactly go faster and slower, like I keep repeating. We also want failover, because there's no point in having this high scalability without high reliability. The more you add nodes, the more the opportunity for a node to fail. Right? There are more nodes, therefore there's more things to go wrong, more connections, more hardware is involved. So unless we have the ability to say, you know, customers 1 through 5 were on node 1, what if node 1 goes down? I need the ability to have failover. Akka with clustering does give you that ability as well. Because if you think about it, if let's say customer 5 is supposed to be on node 1 and node 1 goes unavailable, then the only thing we would need to do is the cluster would need to be aware node 1, which is supposed to have customer 5, isn't available. Fine, create a new node 1 and reinflate or rehydrate or activate customer 5. Now apply the message. Because the state to be able to rebuild customer 5 is embodied in that series of events. Then when you aggregate them all together, there's customer 5 again. We can recreate customer 5 on the fly anywhere. Yes, there'll be a little pause, but it's a little pause. And we've tried this. We'll show it to you. It actually ends up with a remarkable simplicity. I think easy scalability actually is true, because if you try to solve all of these problems with the traditional model with two-phase commit and all of this, A, you don't get the scalability, and it's a lot more complicated. There's an awful lot of things to think about, particularly in a distributed system. This model actually turned out to be much simpler, I think, than any of us were expecting when we first started implementing it. Because to a certain degree, what we're doing is working at a level of abstraction where we're not saying, okay, I need to write code to deal with scalability. We write code to deal with distribution, and we avoid doing certain things, and the side effect is scalability in a certain sense, although side effects are evil. So think about your own domain. This is the interesting exercise, and I'll invite you to do this again at the end of the talk. Think about a problem that you need to solve that requires scalability. And you might have such a problem if you're here listening to me. Consider reads and writes in your system. And this didn't seem intuitive to me when I first saw this. I was like, well, but I always want to read and write the exact same thing. I want to write a customer, I want to read a customer. And strangely enough, that's often not true when you actually dig down to what the operations are. I don't necessarily need to update an entire customer. I need to do something to a customer or an auction or a bid or some other piece of information, some domain thing in my problem domain. Deployment infrastructure is critical to get all of these benefits safely. I won't say that the tuning is trivial. It's not. It's quite significant. In fact, it's interesting how much more significant than with the old model. So, enough theory and enough talk. Let's actually talk about a concrete problem and look at some code. Is the screen keeping up with me, by the way? Okay, great. If the screen goes blank or something nasty, please let me know. Everybody still with me? Make sense? Okay. So let's look at online auctions. And by the way, I want to thank Dave and Katrin. They're at the back of the room. They wrote most of this code. So if there's anything wrong with it, their fault. But quite seriously, the ability to talk to the people that wrote the code, look at the code, take it away when you leave, is here. So please avail yourselves of it. We wanted to give you a real live working example of this to tinker with. So what we did, we implemented online auctions. And we did it twice. We did it once with essentially the CRUD model, but using all of the same ingredients. We just didn't use the DDD model of doing it. We didn't use Akka Persistence because we didn't need it, but we did use Akka clustering. We used the same Cassandra database. The vast majority of the code, I think it's fair to say, is exactly the same between the two implementations. There was very little code that actually needed to change to implement the model. The API, the REST API that we communicate with, is exactly the same. It's the same code. It's not just very similar. It's identical. We just use the same classes. And what we did was we said, okay, let's put it on the same deploy structure. Let's put it on, in this case, on some AWS instances, and let's make the two different versions literally run on the same machines. Not even similar machines, but identical machines. One run one right after the other. And what do we get? If we did one, the traditional CRUD model that I showed you at the beginning, in-place updates, even using Akka, using Spray, using all of the high-performance database and so on, and the other one using distributed domain-driven design and CQRS. So we wrote the CRUD version. It uses Akka, receives a request, writes to the data store, writes to the database. It's a cluster of 3 different Cassandra nodes, writes to the database in the traditional fashion. Very straightforward, right? Nothing fancy about it. This is what the code for that actor would look like. Now, I'm not going to sit here and read you lines of code. It's pretty small. Plus, it's all available out on GitHub. You can read it at your leisure. But what I wanted to do was give you an idea. What's the scope of the code? I'm not sitting here scrolling for 5 pages, right? That's it. That's the guts of the whole thing, with infrastructure and routing and HTTP and all externalized. It may have actually evolved very, very slightly since then, but it didn't get much longer. It's quite straightforward. So essentially what we're looking at is an actor, and you've probably all heard about what an actor is. Basically, an actor is a chunk of code that receives messages asynchronously off of an in-memory queue. In this case, it receives those messages, turns them into some state mutation against a database, and then it's done with that message. That message is complete. We return the response to the HTTP API. So what's different? What are we proposing you do differently to do secure SDDDD? What we're saying is, now there's going to be in-memory state. So that last actor we just looked at didn't have any variables in there at all. It was all completely immutable, e.g. good Scala code. We're actually going to use a mutable variable in the new version, and it's okay. It's wrapped inside an actor. That's the one place where the evil of mutable state is allowed to be contained. We recover that state, that value, the information in that domain object, from a journal on startup. So when that object's instantiated, we read a journal to get back to where we were. Oh yes, I always misread this sentence because it's using a word in a strange place. It uses a thing called become to change states in the particular instance of this actor. And it also does the passivate on timeout. So for example, if we had millions of these, there would only be the ones in memory that are actually required. So here's another actor. And again, you can look at this code. This is the one that's actually in the GitHub repo. It's a little longer, there's a little more meat to it. I won't bore you with line by line, but I will point out up here, if you can see my cursor, line 66, up there. There's a var, a private var. That's the mutable state for the actor being held in memory. So that's sort of where the rubber meets the road. That is my data. That is the state of this particular auction, in fact. Then again, you see messages being received and handled, and you actually see both a receive command, and you see a, down here somewhere, a receive. So, and you see things about snapshots. We're actually using a technique, there's an ability, I mean, if you think about event sourcing, it sounds pretty good and disk is cheap and so on. If you had, let's say, a piece of data for every heartbeat, which actually has happened for a client, and you need to save it, whole lot of data over time, right? That's going to get pretty extreme. That journal does not just append eternally. That may not be a practical instance. There is an ability in Akka to say, when I'm idle, when I have time, when so many events have passed, write a snapshot. That is writing the state and saying, okay, well, now write the bank balance. I'm starting again. And then the remainder of that journal can be discarded. So I can start again from a certain point. How often I do that, when I do that, totally in our control. It's programmatic. You can decide when you want to do that. So there is the ability to truncate the log. They have thought about how to make this practical because, theory and practice are the same except in practice, where they differ. Let's see, there was an passivate in here somewhere too. But I won't keep digging for it. Oh yes, right at the top. Line 115 there actually shows where I receive a message called a ReceiveTimeout. That says, it has not been very interesting for this particular actor, shut down. Effectively, it takes the actor out of memory, queues it up for garbage collection, actually. That's how you reduce from infinite amount of memory, or one times the number of your instances. Okay, so what if we took this code and we actually ran it somewhere? If we had, the test setup that we did this all out on AWS. We used a stress testing tool called Gatling. Great name for a great tool. We quite enjoy it. It's effectively the ability to write a simulation, which you can then run on a separate box ideally, because it takes some processing power, and it beats up on your app for you, effectively. It simulates a series of transactions over a period of time in exactly the way you say, ramp up over a certain time and so on. And then it records the statistics of how long those requests take. So over a period of time, do we get slower, do we get faster, how do we scale? So that's how we measure scalability in this particular instance. There are other tools that do similar things. So we said 3 Cassandra nodes clustered in a database, 3 Akka processing nodes, 1 front-end node, which was also part of the Akka cluster, all on small AWS instances. So we didn't scale vertically here. We didn't throw a lot of hardware at this. And we said, okay, let's use a conservative amount of load, but see how the two models perform independently under the same load. 100 simultaneous users, so 100 simultaneous simulations running, and 100 auctions available. Run that for 2 minutes with people trying to bid against a particular item and see if they win or lose the auction. What does that look like? Here's the simulation. This is actually the DSL for Gatling. Have we got this in the GitHub repo, Dave? I'm not sure. We certainly could. But anyway, this, as you can see, most of it is preamble. The place where the rubber meets the road is really the last line here. 67, you can see part of the DSL, even if you don't speak this DSL. Do nothing for 4 seconds, and then all at once start up 100 users and keep doing that for 2 minutes. So that starts our load and says run for 2 minutes. Nice, simple, small tests that we can see here. What do we get back when we run this with Gatling? One of the nice things Gatling does is it gives you a bunch of pretty HTML embedded graphs as your response. So I've clipped those and made a mess of them on some slides here. I'm no artist, more of a programmer. So CRUD implementation one side, that actor code that you saw, CQRS implementation on the other side. The response time distribution here is a very different shape, and please notice there are 2 different scales, right? This one actually scales up to 25% here, So this is the response time distribution as a percentage of time. So for example, no request took any more than about 301 milliseconds on the CQRS side. There were some that took more than 360 milliseconds on the crud side. And the distribution was quite different, as you can see. A lot more requests were handled a lot faster, although some did go slower, with the DDD side, with the CQRS side. I use those two terms interchangeably. And we did not load it so hard that we got any red lines here. It didn't actually break. You can do that with Gatling, and sometimes that's interesting to go, okay, where is the limit? How much can I, what's the number? How many users can we actually handle simultaneously? We didn't do that. So response time percentiles are also interesting. This is over a period of time, what responses were fast, which ones were getting slower, and how many of each, what percentile. And again, we're going to get a different scale, so I encourage you to notice that this one goes up to 2,000. These slides, of course, will be available 10 minutes after I stop talking, so you can come and look at these in more detail if it's hard to read the numbers on there. But notice the shape. There was a spike at the beginning, and then a fairly high performance. It's not like the crud version of this was particularly non-performant. It was pretty good for what it was. Now the scale is different here. In this case, a lower number, meaning the response time being lower, is more interesting. And you notice the shape of the graph is also very different. The response curves are quite different. Part of that is because of the initial activation of a lot of instances. So these actors getting spun up the first time, because the first time they receive a message, they will in fact be passivated. They don't exist yet. So they go and they try to read a journal, whether there is or isn't data there to read. Doesn't matter. They'll try to read a journal. There'll be a little moment pause, and then that actor will be in memory. How am I doing time-wise anyway? Oh, I'm good. Okay. So like I said, we ran it for 2 minutes. Notice again, the scale is very different here. So how about if we look at it from the perspective of requests per second? And again, Gatling does all this automatically for you. The number of requests per second that we can handle is fairly consistent. It goes up a little bit over time as caching starts to kick in and so on. This is the crud one. And again, notice the scale. We got up to about 1,000 requests. Well, not quite, maybe 800 requests per second with a couple of spikes. Something broke there for a moment. I don't know what it was, but self-healing system. I think one of the Cassandra nodes had a glitch or something like that. Did the same thing when we ran it here as well. But you notice the shape is very different on the CQRS one. It ramps up differently, and you notice the scale. The number of requests per second is more around the 2,800 mark. It's significantly higher. Exactly the same hardware now, right? 99% of the code was the same, just that actor was different. And of course the configuration required to set it up. So what does all that boil down to? What does it really mean if we compare these two systems? The easiest way I find to look at it is how many actual request response cycles did we handle in those 2 minutes, in those two identical scenarios. For the CRUD app, it was just shy of 76,000. For the CQRS app, it was just shy of 200,000. So that little bit of change of code made a fair bit of difference. And I would contend, and I'm pretty sure we did achieve this, that the two are equally consistent, e.g. you won't ever get the wrong answer out of either of them. Because it's an auction-based system, right? You can't afford to have the wrong answer, much like a banking system. Please.
For the CQRS, when is the data written back?
What's the what?
When is the data written back, written to Cassandra?
Oh, immediately after the message has been handled. So in other words, if it's a read operation, in other words, I'm trying to figure out what the price for that auction currently is, then the response would be immediate from memory. If it's a write operation, it would be as soon as the write has been done to Cassandra. So effectively, exactly the same as in the CRUD one, except the CRUD one is doing it on a single instance and reinflating and deflating that instance every time.
So this is basically the performance improvements because of CAP.
The performance difference is because we removed the bottleneck. That is our theorem, and I think we've proven that theorem with the performance numbers that we got. What we did was we removed the bottleneck was contention. And it's interesting, we thought, well, given Cassandra does an awful lot of smart things under the surface, maybe we won't see that much of a difference. At a certain level of scale, you do start to see the difference. Right? You may not see the difference at low levels of scale because you're actually solving the problem by having a really fast database. But then if you start to increase load or make a much smaller instance, reduce the size of the problem, you start to see the shape change. And that's the difference. Is it really just by introducing the idea that there is, because we've separated read and write paths, there's no single point of contention, we suddenly find, and let me show you this part. So what happens if we add more nodes? I'll just tell you this without going into a lot of graphs. The CRUD version, performance increases, scalability increases when you add more nodes for a while. But there's a ramp off to that curve. There's a flat spot after a while where there is diminishing return by adding more and more servers. So up to a certain point, the CRUD instance got a little faster and was able to handle a higher load when we added more nodes. But the CQRS version had not quite, but closer to a linear response to adding more nodes, which makes sense when you think about it, because the journals were actually behind each node. We actually put the journal for one Akka instance on a different node to protect against failure, and it was a Cassandra cluster as well. So it was written to, I believe, at least 2 nodes out of the 3 nodes. Yeah, Dave's nodding. That's the way we configured it. E.g., it is a safe write. We're not saying, okay, the journal is sitting on the same node as the actor, and therefore if the actor goes down, well, all bets are off. No, it is actually a safe write and could recover on another node. Because it's not realistic if we say it's not recoverable. Sorry. That actors crash? Yes. It's very similar to if a single node crashes, but the impact's smaller. Yeah, we tried that too. Basically what happens is that particular instance has to reinflate, which is, it's hard to even see it on the graph, to be honest. When a whole node goes down, if there were a lot of instances on that node, and you're randomly hitting a whole bunch of auctions, yeah, there's a lag. You know, you'll see a little glitch in the graph as it fires back up another node. You don't fail, you just go a little slower for a moment. And of course, the more nodes you have, the less the impact of a single node going down is. You know, that's just the math. Sure.
How different were Cassandra's schemas towards?
How different was Cassandra's key?
Cassandra table schemas.
Oh, the schemas. That's an excellent question. I believe they were not different.
So when you're saying write into a journal, what journal constitutes? Is it also some entry in Cassandra database?
Effectively, yes. It is. We're actually using Akka Persistence, and when I say effectively, that means that what we're actually doing is serializing the case class that represents the message. In the case, so the schema of the finished object was identical. What we're writing to Cassandra was actually quite different. Let me change my first answer. What we were writing to Cassandra in the first case was effectively a snapshot every time. We were saying, here's the value, write it to Cassandra, right, in the traditional way. What we were writing to Cassandra in the case of the CQRS DDD app was delta, 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 a representation of the message. So in other words, if we say a new bid has been received and it's $5, that's what we write. As opposed to the current state of the auction is max bid was $10, right? That's very different.
Records, like snapshot or single web, they don't much different size, as far as I understand.
Not much different size in this case, correct.
So I'm trying to understand where was the contention in the first instance?
The reads, and because of the nature of the test, we're doing a lot of reads and writes to the single instance.
We read from memory in this case.
Right, so, well, no, read. Correct, yeah, what he said was, we read from memory in this case, exactly. I was not intending a pun, to say right. So the CQRS version, what happens if we throw more nodes at that? As you can expect, what happens is we don't have that contention, so we get something close to a linear response to additional nodes. To be honest, we didn't actually take it as far as having 100 nodes to see that it leveled out, but it certainly didn't level out at 5, which is where we started to level out with the non-CQRS version. Tuning, on the other hand, was really important. The first time we tried it, I think the first couple of times we tried it, if I recall, not so much. We weren't doing it right, and we would have problems. If your activation and passivation time, for example, if that timeout is wrong, if your buffer size is wrong, if your Cassandra is set up wrong, you don't get that advantage. And suddenly it's a little worse. But when you tune it correctly, so it is more sensitive to tuning, would be a conclusion I can draw. The CQRS DDD model is very sensitive to tuning. When you start to reach the top of the performance curve with, thank you, Dave, when you reach the top of the performance curve for CRUD, it's not particularly sensitive to tuning. It just won't go any faster at that point. You don't get a lot of response. You can detune it, of course, by doing something horribly wrong, but that's hard. So, to prove that this is all real code, I point you to the activator template. Actually, this is the GitHub repository. There is actually on the TypeSafe site as of about 2 o'clock this afternoon, an activator template that you can use to actually fire up the CQRS DDD version and play with it. And we mentioned the slides will be available, and the exact configuration we used you can reproduce on AWS very inexpensively and give it a try. Prakash?
What are the differences or similarities between the EJB model as far as the activation and
There are some parallels, but they're not actually that similar in the sense that the EJB model still consists of a write to a single mutable data source. Right? It's not, you probably could implement CQRS ES with the EJB model, I imagine. I've never tried it, but nothing should stop you. A message-driven bean, come to think of it, would be the way to go. So it's the pattern that is getting the advantage here. Akka happens to be an incredibly easy, straightforward way to do this, and it handles the distribution better than EJB does because of a lack of single point of contention. But there's nothing about the pattern of DDD CQRS ES that is Akka specific. It just happens to be a really good marriage. They work incredibly well together. Sure.
Are you using the cluster singleton pattern or module in Akka to accomplish this balance?
Cluster sharding in this specific instance, but yes, it is effectively a singleton in that customer 5 is in one place. Sorry, I should be repeating the question. My apologies. Anybody else? Sure.
So in that example, are your Akka actors the source of record of your auction data?
In the transient sense, yes. Are our Akka actors the source of record for our data? And did I represent your question correctly? In the transient sense, yes. The real source of record is the journal. That series of events for that particular auction, that's the true persistent source.
But you still need the actor to have an API into the journal.
Correct.
So how would you interact with systems that are not Akka-based? So
Via that API. So you could treat it like a repository pattern in DDD. Right? You could wrap that in a service and say, when I call this, I want you to go get me the state of that piece of information. You'd have no idea it was an actor on the other end. Right? You don't need to do it. Wouldn't have to be REST. You could actually go, yeah, you'd have, so we're talking about the API. How would you interop this with something that's not Akka? Well, there's not actually anything specific, Akka specific about the API. You could interface to it from Python if you really wanted to, right? There would be no information about it that's specific to Akka. It's just the implementation detail. Well, pretty big detail. Sure, please, back corner there.
What did you guys do for serializing your schema?
I believe we ended up with protobuf, right?
Oh, we actually used it out of the box. We wrote our own using that library, but for this, we're using the box persistence.
So out of the box persistence. That is a pluggable implementation detail. And at high scale, like the nice thing is if we do the same thing on both sides, it's equivalent in this case. But if you really wanted high scale, probably out of the box persistence would not be your best choice. Please.
So in this case, did you have an actor per customer?
Exactly. Yeah, the idea is that per auction, sorry. Yeah, customer was my previous example. Yeah, an actor per auction. It was what we decided was, from a DDD point of view, 3Ds this time, that the auction was the aggregate root. And therefore, there's one actor per aggregate root. Theoretically, there could be literally one actor per aggregate root in memory simultaneously, but that's where the activation passivation comes in.
So as part of the journal, are you keep a journal per auction, or are you keeping a journal for a single journal for all auctions?
Logically, it's a journal per auction. Actually, what happens physically is tunable. So for optimization purposes, is that a single Cassandra collection or is it multiple? Your call. In fact, it's a pluggable persistence mechanism. So the way that happens, and we're using snapshots, which is to yet another Cassandra table. So you have a choice, is the short answer. Please. Back there.
everything didn't show any number, extra scalability number. You only show the performance part. You show how you scale with the number of nodes.
I'm sorry, did I show something that scales the number of nodes?
You show the Gatling, you show a functional graph, right? But
Yes.
I would say that's more performance.
It is more related to performance, agreed.
But they didn't show how you actually scale
I do not have graphs for that, quite correct. Yep. Feel free to grab the activator template and fire it on AWS and just change the number of nodes and you can see how it reacts. That would make a good picture, my apologies. Sorry, the question was, after the fact, that we didn't show actually increasing the number of nodes. So what we were showing was more related to performance, but a measure of scalability because we had that number of transactions. Go ahead.
Cassandra internally is a append-only system, right? So internally it's also using journalism. So how is it? What is the point of contention?
Yeah, you were saying that Cassandra internally is append-only journal anyway, to a degree. There's actually a write-in-place update eventually in Cassandra. It updates internally, and that's one of the, actually a lot of databases do exactly that, interestingly. Even SQL databases internally do that. It turns out that you can get better scalability by, in essence, doing that yourself, as opposed to outsourcing it to your database. Because the database is actually trying to give you an abstraction that looks like right in place. So therefore, you kind of artificially introduce a point of contention, is what we found, even with Cassandra. And we purposely use Cassandra in order to eliminate that as a possible source of the problem. You know, to go, okay, well, what if we used a better database? Because if we did this with MySQL, you'd be saying, well, why don't we use Cassandra? So we thought, let's use the best tools we can and see if there's still a difference. And this is what we found. Please.
Sorry.
No problem.
Someone else.
Okay, sure, we'll come back.
Again, how essential Cassandra as a choice of the database in this perspective?
It is not
Or
essential.
transaction?
It would be the same issue, I believe.
Would you say you would build a banking system based on this application?
You certainly could. Yeah, you certainly could.
You can give transactional guarantee.
Well, it's a non-transactional guarantee, just oddly enough, right? In the sense that I would state that there is actually not a transactional boundary here, because each of the events are idempotent and individual and atomic. So the event, if anything, is the transactional boundary, is really what it amounts to. If you have to put a transactional boundary around anything, it's really the event. And there is a certain sense of eventual consistency, of course. Very short eventual consistency. Sorry, the question too was, could you do this with any other database? Could you do it with Oracle? Could you do it with Postgres? Sure you could. Absolutely. The choice of persistence, one of the only reasons we picked Cassandra is it's a high-performance modern database, and we wanted to eliminate the database helping us as the only reason the performance numbers changed. So we wanted to use the same one. Please.
We have a system that has a message broker in between, like for example RabbitMQ.
Right.
Not a replacement for that, or?
That's a really good question. Is Akka a replacement for a message broker like RabbitMQ? The short answer is not exactly. And I know, sorry, that's a little vague. What I mean by that is that there is the concept for every actor of a mailbox, which in essence is a queue, right? There's a queue that is coming into the mailbox. But that queue, without Akka Persistence, is in fact transient. It's not a persistent queue. RabbitMQ has the ability to externalize that queuing and do, for example, pub/sub much more readily, interop with other systems that may not be Akka-based and so on. In a pure Akka situation, I'm not sure you would necessarily come across a need for an external queuing system, but we have certainly seen it done with RabbitMQ, ZeroMQ, Kafka, many different external queuing systems that have their own advantages that may be required for some other aspect of the system. But you certainly don't need an external queuing system to do this, to do DDD, CQRS. It doesn't need to be external. It could be done within Akka. Please.
How easy would it be to plug in to Akka Persistence different queuing system?
Actually, I think really hard. Sorry, the question was how easy would it be to plug in a different queuing system to Akka Persistence? I know there are many pluggable implementations for Akka Persistence, and I believe someone was tinkering with one for Kafka. But right now I believe it's LevelDB, MongoDB, they're all databases in other words. So it's assuming that Akka needs to be able to handle its own persistence, its own events, but so to my knowledge no one has done that yet, but I believe it was being worked on. It may not be as hard as I think. There is already a plugin for Kafka, then I take it back, it has been done. So there, pretty easy. Please.
Can you say that the difference between CRUD example and DDD is similar to the difference between stateless service-based architecture and distributed object cache. What I see is basically cache to memory hub.
A little bit. That's part of it. Sorry, the question was, is the difference between the CQRS and the CRUD architecture like the difference between a distributed in-memory cache and an update-in-place architecture? And a distributed in-memory cache moves the problem higher in performance, but not in scale. You still contend. There's still one place, even if you used, rack or something, where you say, okay, I need to update that entry. At a certain level of scale, there's still going to be enough reads and writes that contend to get that value, and you have to be transactional around that value. So our impression, and who knows, we might be wrong, is that those two are not the same. Like, that doesn't make the problem go away in the same sense that CQRS ES makes it go away, by removing the contention.
But here, you still have one entry point which decides how to find the object that this message is addressed, right?
Correct.
So it is...
The cluster controller.
Yes, similar entry point.
But
where to find the cached object, or where to find the real...
It's when the read and write takes place on the cached object that the contention occurs. It's on the other end of that process. The routing happens one way or another. So our experiments so far seem to indicate that a distributed cache does not give us the same level of scalability. It's not enough. All it does is we go faster, and then we hit the curve. So it moves the graph up, but doesn't make the graph flatter. It has been our experience in any case.
What kind of mechanism would you use to route
Actually, that's built into Akka clustering. The cluster sharding plugin or capability for Akka does that for you. You actually give it a pluggable function that says, given an identifier for this message, e.g., which auction do I go to, this is how I figure out which shard you're going to go to. And then you decide how the sharding algorithm is going to happen. It's very much like database sharding when you cluster a database. It's very completely analogous. Sure, did you remember your question?
Do you deal with either business domain changes or data model changes?
Oh, that's a good one.
So what I'm wondering is, in the traditional update and replace model, what you would do is, if for whatever reason your data model needed to change, would run a migration over all your data, and going forward, all operations would use
would now look like that, yeah.
So how do you handle your existing log entries, or whatever the term should be?
Yeah, that's the reason that's such an excellent question, and let me repeat the question. How do you handle effectively schema changes, right, is the short way to say that. So my business domain has changed, and let's say the messages that I'm going to receive, if it's in a message-driven environment, need to change. There's a new field, there's a different field, the meaning of a field's changed. That happens, right? Over time, things migrate. That gets more complicated with this model, I will admit. And the short answer to how we've dealt with it, and I'm not saying it's the best way, because I think it's still a topic of research, is don't take fields away. So in other words, a better way to say that is, if you have an old message that says, here's how I update a balance, then I have a new message that says, here's the new way I update a balance. Ideally, your actor should be able to handle both, until there are no more of the old message in the journal. So if you snapshot periodically, let's say you snapshot every day, then if it's been a day since the last time you've used the old message, you'd be okay dropping support for the old message. It's a very delicate dance. That is tricky. It's also very important, if you change the schema of the message, that you can still deserialize the old ones. We have shot ourselves in the foot with that once or twice. By changing the serialization format and then going, whoops, replay the journal, you're deserializing messages that aren't in that format. New required field, problem. The old thing doesn't have it, boom. So yes, that is a delicate dance. It is similar to the problem that you have of saying, okay, I need to migrate my old data, in that one way to do it would be migrate the old events. Right, you could just treat those as your record and say, okay, I've added a new field, I've taken a field away, just modify the existing events. That's considered bad style. As Jonas's talk said earlier today, don't change the past. Be a considerate time traveler and don't go back and change facts from before. That journal should be immutable. Truncatable, but immutable. So that, yes, hard problem. In fact, it's probably going to be an additional part to this talk in the future, is how do you deal with schema changes over time? My apologies, please.
I'm wondering if you have any experience using Apache Camel for your external...
Apache Camel?
Yeah.
Most certainly, absolutely. I think of Apache Camel as the ultimate manifold. You know, it has plugs and pipes for just about every kind of protocol that you can put on a stream or a queue. Not between actors. What I've used it for is external messages or events into the actor system. So it's better the way actors handle messages asynchronously with mailboxes and so on. It's better to let the actor system handle that. That part is not pluggable, to my knowledge. That's the way it works in Akka. But to plug things into Akka that happen to be event-driven, Camel is a wonderful tool for that. And I've used it many times. Please, here.
I'm wondering, how would you aggregate state across multiple actors?
Also an excellent question. How would I aggregate state across multiple actors? The reason I say an excellent question is it's still a topic of debate how to do that best. It's tricky. The tricky part is identifying correctly the aggregate root. So that's why DDD comes into this. That's the domain-driven design part. You have to understand what is the parent object and what are child objects of that parent object. Right? Because at some point when you're making a cross-object change, you're saying what I'm affecting is actually a larger thing that happens to have these smaller things inside it. And then model that as your actor. Okay, that's another way to say it, is you don't. Yeah, there is no two-phase commit, so to speak, in this picture. There's no way to say, I want to update that one, and only both of them together, never only one. What you would do is aggregate both of those things into a single actor, two different pieces of state, let's say, in that one actor, but that's modeling the aggregate root then, and there's the atomic change, just as we said when we were talking about what's the transactional unit, the atomic change is the message. So when I hit that message, I can mutate state all I want inside that actor, because I will not handle another message until I'm done with that message. So it's safe, right? You're in a safe little world where you can say, don't worry about asynchronous stuff. That's not happening. I can update this, compute that, change this, update a state. Now I'm done. Now the next message. And if that happened to update many different pieces of state in that actor, no problem. So that's why the DDD part is so critical. Evaluating what is the aggregate root is really what it's all about. As soon as you've picked the right aggregate root, things start to flow. If it seems very, very difficult, you've probably got the wrong aggregate root. Well, I think we took a couple of cracks at that, actually, even for this simple example. Please.
Just following this question.
Sure.
This is mostly about Akka, not this particular mechanism, but what happens when the actor receives a message? Then it fails to persist in that. Is this message lost?
If you don't take any extra effort and you send a message to an actor and the actor fails to handle that message, the message is lost. And it is lost. The if there is a big one though, because there are many things you can do to make that not happen. Right? There's acknowledgement, there's Akka Persistence, so you can have everything that comes into your system received by one actor, which is then persistent before it sends it for computation in the whole system. So now there's another journal involved, which is now the incoming requests for your entire system. Those are persisted first, and only if they're handled do you get a response, otherwise you get an error. So yes is the short answer. The long answer is it is possible to make the system completely persistent. So the trick is to have, you may tune your level of guarantee. Do you need guarantee only once delivery? Do you need guarantee at least once, which is the most common one Akka Persistence will give you? Or do you guarantee at most once, right? The lowest level of guarantee you need, the higher the level of scalability you can get, right? It's a trade-off just like this. The less guarantees, if you need order, for example, suddenly you've got a bigger problem and your performance and your scalability will go down. If you don't need order and things can be idempotent and handled in any order, you can scale to the moon. And so it's all about what guarantees you need. It is a fine art, no question. Yeah, there's nothing about this model that's magic or solves the world's problems. It's one more tool in the toolbox that works in many situations. Better than we kind of expected it to in many situations. Anybody else? Questions? Comments? Tomatoes? Anything? Here.
So these are some insightful answers to some important questions.
Are you available for consulting?
Excellent question. Indeed, not only am I available for consulting, but my entire team is available for consulting. This is what we do. We come in and we solve problems like this and help your team know how to do it. Yes, we will, in fact. And I do invite you, and thank you very much to both Dave and Katrin, who are at the back of the room. None of this would be possible without them. They wrote basically all of this code. So I do invite you to speak to them and drop us a line, send us an email. My email was back at the beginning. It's michael.nash@boldradius.com. Do drop me a line if you have questions, because I know what it's like. You leave this session and you're like, oh, how the heck did that work? Drop me a line. We don't mind. It's great. And if you need us to come and help your team learn how to do all this magic, you know where to find us. And thank you very much for hanging in there and coming out this evening. Thanks.